Module 9, Avionics and Electronic Display Systems. This is, for me, one of the most interesting parts of this entire presentation. Okay, so let's start at first with the evolution from analog to glass cockpit. Okay, early aircraft relied on individual analog instruments, each dedicated to measuring a single parameter. There was no integration and no digitization. These instruments were mechanically or electrically driven and required extensive pilot cross-checking. Okay? Why? Because they are separated from each other. Each one is located in a different site. Now, the development of digital electronics enabled the transition to integrated avionics system, commonly referred to as the glass cockpit, meaning that you can have such is such as for the case of the ECAS and the ECAM, different displays within the one or on one screen, one integrated screen. In glass cockpits, multiple parameters are processed by computers and presented on electronic displays, reducing pilot workload and improving situational awareness. Another side note I want to talk about is the term situational awareness. So, what does it truly mean? Situational awareness is the understanding by the pilot of the different conditions of the airplane when it comes to the attitude, okay? So, whether the aircraft is pitching up or down, if it's rolling to the left or to the right, if it's skidding, okay? That's one. Second, the airspeed. And third, the altitude, along with the VSI, vertical speed indicator, so that, and also you add to that the navigation, like location wise, when it comes to the heading, the location, the navigation related parameters. Okay, so these are the main premises, the most essential type of data that the pilot needs to be aware of, and they need to be clear and intelligible by the pilot so that he can understand where he is on the map, what is his heading, his altitude, his whether he is in a leveled flight or if he's climbing or descending, okay, which is given by the VSI, the altitude again, and the attitude, whether he's in a roll to the right, to the left, or whether he's pitching up and down. This is what we call situational awareness. Another note here is most instruments used to, like during the early stages of flying throughout history, okay, for smaller aircrafts, they used to be mostly mechanical. Okay, the electronic systems and electrical were gradually introduced afterwards. This evolution allowed centralized data processing, improved accuracy, automated alerts, and system redundancy instead of single sensor, single display architecture. Okay? Modern avionics employ multiple sensors feeding shared display systems. For example, here in this image down below, you have the attitude indicator, okay, at the same time skid or slip indicator, which is this one. So when it's moving away from the upper arrow, when the lower white arrow is moving away from the upper arrow, you would notice or you would understand that there's a slip phenomena going on, whether to the right or to the left. You have to the right here the altimeter or measurement of height, VSI next to it, which is the vertical speed indicator. It would be 0 in leveled flight. Okay. And to the left, you have the ASI or airspeed indicator. Also here, turn coordinator, and the HSI, horizontal situation indicator, which is the compass commonly known. Okay. Slip and skid indicator here, as you've seen. Okay. Turn rate in degrees. So yeah, this is the turn rate here via the turn indicator. So all of these instruments are integrated in one display. Okay? Of course, definitely they are not simply one instrument. No, the reading, the display is integrated on one computerized screen. Now, note that in order to have redundancy, you would also have some of the instruments in analog format in case the screen fails for some reason, okay, or the computer malfunctions here. And to add to that, you would have different types of alerts, such as the stall alert and other types of alarms appearing on this very same screen, like when you have a retard in the engine, which is a maneuver during landing that was installed by Boeing. I don't remember which year, okay? And if they had changed it, and you have like the stall warnings. Yeah, different types of alarms would be indicated on this same screen as well. EFIS, or Electronic Flight Instrument System. The EFIS, or Electronic Flight Instrument System, replaces traditional flight instruments with electronic displays driven by digital data. EFIS integrates inputs from pitot-static systems, inertial sensors, magnetometers for like the navigation, and navigation sources, okay? Inertial sources to get the slip and other parameters, and the RPM, for example, okay? Yeah, you have air data computers, ADC. This is the like what makes the architecture of the FIS, the air data computer, attitude and heading reference system, AHRS, the display units, data buses, and processing units. Now, the sensor data is sampled, digitized, and filtered before being displayed. Okay, the sampling frequency, meaning that you have the signal is broken down into different samples, and these samples would be coded with the binary system before being like translated or converted into useful data. The sampling frequency must satisfy the Nyquist criterion, which is Fs. Okay, that would be the sampling frequency, should be greater than or equal to 2 times the maximum frequency of the signal being collected, okay, of the frequency of the signal of the message, okay, or the parameter that's being measured, in other words, where Fmax is the highest frequency component of the measured signal. Now, this is how it works, because it might have seemed ambiguous here. Okay, so you have a measurement of the temperature from the EGT, for example. This is the signal being collected from the EGT. Now, in order to convert it into a digital value, I need to break it down, okay, to take samples, because you cannot digitize all of, you have infinity of values within this analog signal. So I need to break it down into samples, okay? How to break it down? I should like run a sampling frequency. This is the Nyquist frequency of sampler that we're talking about, okay? Which is the inverse of the period of that sampling signal, okay? Fs is equal to 1 divided by t, and the period being the temporal distance between between two peaks or two troughs, okay? So that would be the sampling frequency. Now, this sampler, whenever is multiplying the signal and its value is 1, because it is a sequence of 1s and 0. So whenever the value is 1, what you get is a part of the signal. When the value is 0, you get nothing, okay? So let me try to make it clearer. So this is the signal, this is the sampler, correct? Okay, so when the signal is multiplied by 1, the value is kept. When it's 0, there would be no value, so you would have, okay, a chunk of values based on the sampling frequency. Now, these chunks are also quantized. Quantization meaning you take only one number from each chunk, okay? And that number should be, I'm sorry, this is sampling here, okay? Normalization, you take one value from each sample. Then quantization, this is what quantization is about. So you would have a preset number of values for the amplitudes from 1, 2, 3, 4. Okay, these are different preset amplitude values for the signal. Now, if this sample is closer to 4, okay, it would take the value of amplitude 4, okay? If it's closer to 3, it would be snapped to 3, etc. Now, for each quantized value, for each like level in the quantifier, you would have a different binary code. So let's say at 1 you have 001, at 2 010, 3 011, and 4 100. Okay? So this signal becomes, how does it become a binary sequence that can be understood by computers, which is the point. The 4 is sent as 100. Here you have, for example, 3, so 011, okay, as a sequence. Then you have here 2, which is, it's called 010. Then you have here 1001. Then it goes up again 1001. Then 2010, 3011. Okay, so that sequence, when it's read by the computer, it can understand the level of the temperature at each moment and display it on the screen. And also it can now process it and analyze it, because this is what computers do best. They can analyze info and produce alerts based on this info if the values that are being measured are beyond or outside of the normal ranges of operations, okay? And they can fire an alarm or a master caution, for example. PFD, or primary flight display. The primary flight display presents essential flight information in an integrated format. Typical PFD elements include the attitude, the airspeed, altitude, VSI, and heading, which is, by the way, what we've seen some few slides ago, okay? That integrated screen, this was the PFD, primary flight display. Now, these parameters are computed using data fusion techniques. For example, airspeed is derived from the pitot static pressure inputs, and this is how we measure the airspeed. We've seen that formula, I believe, before. V is equal to square root of 2 times a total pressure minus static pressure divided by rho. Attitude information is provided by the AHRS system, attitude heading system, AHRS systems using gyroscopes and accelerometers. The attitude solution relies on sensor fusion algorithms that combine inertial measurements with gravity and magnetic references. Now, as a reminder on how we get the value of the velocity, so you have total pressure is equal to dynamic pressure, at first static pressure, which is PS, plus dynamic pressure, which is Q. Now, dynamic pressure is equal to what? Q is equal 1/2 rho V square, with rho is the density of the air, ambient air, and V is the velocity of the flow, okay, of the airflow. So, if you place it here in this equation, you get PT minus PS is equal to Q, which is 1/2 rho V square. So, rho V square is equal to 2 multiplied by PT minus PS. Hence, V, the velocity, would be equal to the square root of 2 multiplied by PT minus PS divided by rho, which is the density. MFD or multi-function display. The multifunction display supplements the PFD or primary flight display by presenting secondary and situational data. Typical MFD information includes navigation maps, engine parameters, weather data, which is in the weather radar, and system synoptic pages. Now here to the right, we only see the primary flight display or PFD because we don't see any maps, any engine parameters. They might be showing on one area or another that I'm not aware of, but this is the PFD. The MFD includes the PFD, okay, and other things such as the map and the weather data, which is not showing in this picture. Data refresh rates vary by parameter type. For example, engine data may update at slower rates than attitude data, which needs to be in real time for the situational awareness to balance processing load and display stability. R update, which is like the frequency of update, is the inverse of the period at which the parameters are being updated, which is 1 over T. T is the period of refreshing or the time lapse between two checks or two refreshing events of the data, or in other words, like the time lapse of a cycle, a complete cycle between the first refresh and the second one, and the one right next to it. Sensors, data buses, and integration. Modern avionics rely on distributed sensors connected through digital data buses. Common avionics data buses include ARAINC 429, ARINC 664, AFDX, and CAN-based systems. Data throughput on a digital bus is defined as D equal RB multiplied by N, where the data rate is D, okay, RB is the bit rate multiplied by the number of active channels, okay? So the number of active lines or active channels, you multiply it by the bit rate at each channel, okay? Because the bit rate is the same for the different channels, okay? It's stable. That would give you the overall data rate, for example, in megabit per second when we talk about the internet. It won't be that fast for aircrafts necessarily. Now, system integration allows multiple displays to access the same sensor data, enabling redundancy and revisionary capability to cross-check between two instruments displaying the same value, the same data, each one operating in a different way. One is a monitored computer, the other would be another type of electronic instrument. This architecture reduces wiring complexity and improves fault isolation. In this display, we have an aircraft sensor cheat sheet. Now, bear with me because it's not high resolution, but I will try to break it down. You have different sensors for different functionalities within the aircraft. For example, the air data sensors such as the pitot tubes, the static ports to detect the static pressure, angle of attack or AOA vanes, which are, mounted, at the front. Okay, these would turn based on the angle of attack to actually measure the angle of attack of the air against the aircraft, against the fuselage. Total air temperature, TAT probe, okay, that would be a resistor that would change based on the temperature. Now, second, you have engine sensors such as the EGT probe or exhaust gas temperature, N1 and 2 speed sensors that are, like they measure the speed of the engine based on the alternative or the alternators, okay, based on the current or the frequency of the current being generated by the engines. Fuel flow and reservoir sensors for detection of level detection based on the capacitor level or mechanically. Then vibration sensors, okay, for the vibration detection. You have navigation and positioning sensors for GPS antenna, radio altimeter, inertial reference units, IRUs, for the geolocation, and weather radar. Finally, you have landing gear and braking sensors for the landing gears, like squat switches, okay, proximity sensors, proximity to the ground. This is during the landing when the aircraft starts sounding 50 feet, 40, 30 during the landing before touchdown. Brake temperature sensors to detect the temperature of the brakes. Environmental and safety sensors such as the smoke detectors, of course, cabin temp sensors, and ice detection. Now, to the top left of this slide, we observe the illustration of the AOA sensor. AOA, of course, stands for the angle of attack. And this type of sensors works by measuring the shift in the capacitance value of this inner part of the sensor that would be on the inside of the aircraft, and the part sticking to the outside is the rudder-like winglet that would change direction based on the airstream or the airflow. So if the air is streaming in this direction, it would turn in the same orientation, okay, to face the air. If it was facing sideways, if the air was flowing in this direction, this wing-like structure would turn around, let's say, 30 degrees up, okay, to follow the stream. And this is again how it measures the angle of attack by measuring and comparing the shifts in the capacitance value. Because if you remember, the value of capacitance is given by epsilon times A divided by D, with A is the area of the armature that is housing the magnetic field, okay? One of the armature, not both of them. And D is the distance between these armatures, okay, in meters. Epsilon is the permittivity, okay, which is the electric characteristic of the material between the armatures. In such case, that would be the air. At the bottom left, what we have is the stall sensor. Now, this is how it works. In normal operation, the air would be streaming and flowing normally around the wing. And by the way, this sensor would be attached at the leading edge of the wing. So imagine that the wing is like this, okay? This is the wing of the aircraft. This is the leading edge, okay? So this is the direction of the wing surface. This stall sensor would be installed at the leading edge, and this is how it actually works. So let me erase a little bit over here. When the air is flowing normally and without disturbance, like when it is flowing in a laminar flow characteristic, okay, which is around the trailing edge. This means that the aircraft is generating lift, okay? At least it's maintaining itself, it's being maintained on a leveled or controlled leveled flight, okay? Whether leveled or in a descent, but the wing, in other words, is still generating lift, okay? And this is how it will work. So as long as the air is flowing normally, it would keep this switch-like sensor pushed down, okay? Now, however, when you have a stall condition, what will happen is that the air, instead of moving around the wing like this, it would move upwards, okay? The moment it moves upwards, what would happen is that this switch over here, it would go up, okay? It would become like this within the sensor. So it will move up, activating the stall warning, which would be like, for example, if it's connected to a stick shaker, it will activate the stick shaker. Or in this case, to the right, this switch, when it goes up, it will open a cavity, allowing the air to flow within a tube, and that tube would be connected at the end with a horn. And the horn would start, screaming. It would start whistling, indicating a stall condition that is affecting the aircraft, and this means that the aircraft is at a precarious condition, about to lose lift and to fall from the sky completely. Okay, so this is very important to warn preemptively the pilots so that they can take the proper action in order to avoid the aircraft a full stall where the aircraft would fall from the air. And now in such case, what the pilot should do is lower the nose and increase power. In fact, you increase the power first, then you lower the nose in order to gain more airspeed. And when you have enough airspeed, the flow would go like this, pushing back the button downwards, and this is what will clear the stall warning. And the aircraft would gain enough momentum within the air, it would gain enough airflow that can guarantee keeping it airborne. Failure modes and reversionary displays. Despite high reliability, avionics systems must account for sensor, display, and processing failures, because these things can fail, whether they're mechanical parts, where it applies, of course, or the electronic components, where you have sensors relying on electronics, or the electrical connections, wirings, and other devices. Common failure modes include sensor disagreement, meaning that you have conflicting data or conflicting values coming from two sensors on two instrument displays that are measuring the same value actually, okay? They are working as a redundancy. Or display unit failure, so the unit is failing, like the value doesn't make any sense. Data bus faults, meaning the connection, electrical connections, or the data bus that is relaying the data from the sensor all the way to the indication systems has a faulty connection or is problematic, or you have a short circuit. And power supply interruptions, so when you have a power failure, like for example, two engines or both engines flame out, okay, during a flight with the heavy aircraft type, what you would have in such case is like the interruption of display. Okay, why? Because these instruments are mainly powered by electricity. Reversionary modes automatically reconfigure displays to present essential information following a failure as a backup. For example, a single display may assume both PFD and MFD functions. Okay, it can integrate both PFD, primary flight display, and multi-flight or multi-function display functions. Fault detection relies on comparison logic and voting algorithms. And this is how you judge it. Let's say you have two sensors collecting the same type of data. Okay, we have two sensors for the purpose of redundancy. Now, how can we judge whether a value is correct or not? Okay, like how do we assess whether the measured value that's being displayed is accurate and acceptable, or in other words, valid, or should it be rejected? X valid is equal to 1, or a measured value, would be voted as 1 as acceptable when the difference between the two measurements, which is xi minus xj, okay, so the distance or the excursion between these two measurements coming from the two sensors should not exceed epsilon. Epsilon in such case is the allowable tolerance. In case the difference between the two measurements is much larger than this epsilon value, okay, which is a small, tiny, acceptable gap between the two measured quantities. If it's larger than epsilon, then the value, the measured entity, should not be taken into consideration and the value should be rejected otherwise. Operational considerations and limitations. While glass cockpits enhance situational awareness, they also introduce new challenges, such as automation dependency and failure management complexity. Okay, so it's much more complex to troubleshoot in such case. Pilots must understand system architecture, reversionary logic, and backup instrumentation to ensure safe operation under all conditions. So if the PFD and MFD fail, pilots should be able to rely and to be able to understand and read the other instruments that are backing up the PFD and MFD, which is the primary flight display and the multifunction display. PFD is part of the MFD actually. So in case of a failure, and more than that, in case when you have an emergency that requires a manual operation, the pilot should be aware to disconnect the autopilot. Why? Because the computer systems would rely on these measurement data in order to automatically fly the aircraft. In case these values, these measurements, and the sensors, one or more of them are faulty, so the autopilot would be operating on false premises, which can bring down the entire aircraft or cause like dangerous maneuvers to take place. So that's why the pilot should understand when to disconnect the autopilot in case you have an emergency as such or like an incorrect sensor reading.